Let's go. Integrated rate laws is where we left off yesterday. We talked about how to experimentally determine using tables of data and different sets of experiments to figure out a rate law. First and second order integrated rate laws are slightly different. These things use experimental data that has been graphed, right? So we take the concentration of something versus time, and we look at the data that comes out. It may be something that looks like this. It may be something that looks like this. It may be something that's kind of all over the place. That's a problem, right? Our goal is to find something that is a linear relationship so that we can actually make a determination as to what a concentration is at a specific point in time, okay? So for the first order, what we did is we took the natural log of the data and we graphed it, and if it comes out to be a straight line, then we know that the data is correctly been treated, right? And that's how we can determine if something is first order with respect to that specific reactant. Yes?
Isn't it like the R value is like the closest to 1 also?
Yes. So when we did this in Excel, we used a correlation coefficient, which is what you are talking about.
Stats view from Melville is.
Does that say?
I hope. You know what a correlation coefficient is?
It's actually one.
Did they make you, did you at some point have to describe what it means?
Well, it's just like, it's basically like a rating of the linearity, basically. I don't know exactly.
It's how closely data actually follows a line,
Yeah, trend.
right? That's what it is.
Of course.
So what we're talking about here is the actual mathematical treatment of data includes a correlation coefficient. The closer this number is to 1, that's how much the data fits the line that you're trying to make it fit into, okay? And so when we did this, we would make a graph of the natural log of concentration versus time. And if it came out straight, then it meant it was first order. Woo. Okay? For second order data, the treatment was the inverse of the data. Again, if we graphed 1 over concentration versus time is always on the x-axis, and we got a straight data, then this would be a second order. Things to remember. What does that mean? At a certain time, right? What does that mean? Initial. Okay.
Yep.
The rate constant. 9 times out of 10, the reason we're doing this is to determine what the rate constant is, right? Because the slope of each of these lines is going to be the rate constant. I'm going to do this one backwards. This graph should have a negative slope. Yeah.
On the left side of the first order, what is like right next to the concentration? Is that T?
A sub t, yeah.
Okay.
Now, how can I ask this question on a quiz or a test? I can give you, like I did on the quiz over this section, 3 different graphs and ask you which of these is the one that you would choose, given correlation coefficients and equations of the line. I would highly recommend you go back and you find that quiz and you look that over before your test. I have been known to put that exact problem on your test. Yes.
Are we gonna have like all the ones open online?
Yes. I will do that this afternoon.
All of mine were.
Were they? Some of them I went through and did, but some of them I might not have, like the recent ones. The recent ones had not been taken. If they haven't been taken by everybody, I can't open them. So there's one I think I can't open, but I will make the answer key available as soon as I can. Right? If they are on paper, I will go through and I'll find my answer keys and I'll put them up in case you don't get them back in time, right? It's one of the things. What other questions? We good? Okay. The last one was zero order. What did a zero order look like? So zero order was the very basic concentration versus time, and it would have a negative slope if it was zero order. And it's just straight that. So you wouldn't have to manipulate data if something was zero order. If something is zero order, does it have anything to do with the rate law though? Remember, if we get a rate law, say we get this. Does B have anything to do with the rate law? No, because any number raised to the zero is just 1. So if you get something that is zero order, it means it has no impact on the rate law whatsoever. So a lot of times when we look at zero order graphs, if something is zero order, it has no impact on the final rate law. So it's not very experimentally useful, right? Really all it's there for is to tell us this has nothing to do with the rate law. All right, next up, half-life. This was the introduction of half-lives, believe it or not, in chapter 14. We talked about 2 different half-lives. There was the first order half-life, which is what we then used in nuclear chemistry to assume that everything decays by a first order half-life. And then we talked about second order half-life. So there's our first order half-life equation. In solving this particular equation, we can solve for the time it takes for half of a sample to decay, or we can solve for the rate constant if we know that information, right? You would have to know one or the other in order to use this particular equation. The second order half-life looks a little bit different. It has a actual calculation and does not involve a standard number. So if you had something decaying by second order, then you would need to know the initial concentration you started with. And you would need to know the rate constant, or you would need to know the half-life. Right? Okay. Moving on. Temperature and the impact of different things on our kinetics. So what does temperature do? And this is still 14.5. Yup. So what should it do to the rate of a reaction?
Speed it up.
Should increase the rate when T goes up. Basics. All right. And this is all based on when we speed up molecules, what do they tend to do? They collide.
Woo.
This is collision theory. Okay. Please remember that collision theory is based on 2 factors. How they hit and how much energy, so how hard they hit, right? How they hit meaning orientation, and how hard they hit meaning energy. We also then introduced the idea of activation energy. Ooh. Ooh. Are you impressed? All right. In this same section, we introduced the idea of activation energy, which means we also had to talk about reaction coordinates. Okay. Hopefully you recall something along these lines. A lot of times we started with our reactants and our products. We measured the height of the hill, and we called this the activation energy, aka the amount of energy required to get the two things to actually collide, or stick, or reorient themselves, react, etc., etc., etc. We also then talked about the difference in energy from the starting and final positions, and called that change in energy. Okay. How do we lower activation energy? And there's really only one good answer.
Decrease the temperature or what?
Nope. There was a special thing called a catalyst. Remember, a catalyst lowered activation energy barriers. Activation energy? Is that what you're asking?
The EA?
Activation energy. E sub A.
East. Okay.
It's like a small one. It's like,
Yeah, I gotcha.
that's how you write it.
It's
So EA decreases when we have a catalyst, but delta E stays the same. We're doing the same exact reaction. All we're doing is we're adding in a catalyst. And we talk a little bit further about catalysts later on. There were some stray equations here. The important one is that if we graph the natural log of a rate constant, so say we do several different experiments at different temperatures, if we graph the natural log of K versus 1 over T, and this is Arrhenius, in case you're wondering what I'm talking about here. There is an Arrhenius equation. This is an Arrhenius manipulation. The equation itself doesn't matter so much because if we can use a graph, we're going to use a graph. All right. If this data comes out the way we want it to come out, remember this is several temperatures, same experiment, several temperatures, measuring the rate constant for several different experiments at different temperatures of the same exact reaction over and over and over again. The slope is then going to equal the activation energy over the gas constant. So this is an Arrhenius manipulation. This is the only real way we used Arrhenius. If you're interested in the Arrhenius equation, the original, it says that the rate constant is equal to an Arrhenius constant times E to the, is it okay if I write the little caret so that you know what's going on here? Okay. To the, I'm going to do negative EA over RT. This whole thing is the superscript. Make sure you understand that. This is the actual Arrhenius equation. Again, the useful thing that we can do with this is manipulate it to get it so that we can use the data experimentally, right? If I can get my data here, then I can calculate an activation energy using a slope. That's pretty useful. All right. Aside from that, reaction mechanisms. You remember slow, fast, fast, slow? That's what's next. Oh no!
Oh no, chemistry.
What does the upper
We're going to do a fast one. I'm not going to give you a slow one on a final exam. You don't have enough time.
What does the capital A stand for?
What's up?
The capital A in the Arrhenius? Yeah. Is that the concentration of the
Say again, I'm sorry.
A, capital A.
The capital A, constant. It's the Arrhenius constant.
Okay.
Which is why I say this is not as useful to us as that is.
All right. And
This manipulation of this data is much more important to us.
And is that caret saying that that's
This is all the superscript.
Okay, I was
This
gonna say,
whole
yeah.
thing. Yeah. Can I erase this? Can I erase that? Are we good?
And then
What's up?
I don't remember.
This is all chapter 14.
I know.
We are still in chapter 14, guys.
I don't remember that. I don't remember
We are moving on to section 6 of chapter 14.
Oh,
What did
okay.
E7 stand for again?
Face energy.
I will tell you my goal today is to get through chapter 19.
Energy.
Oh, then we better keep
Yeah.
going, huh?
Oh, we have.
My goal is to get through chapter 19 today during class. After chapter 16, things speed up considerably.
It'd be tragic.
But 14, 15, and 16, there were a ton of topics, and we spent a long time on these chapters on purpose. We're talking, these are the chapters that we spent 3-4 weeks on this semester. Okay? Chapter 13, not so much, but chapter 14, 15, and 16 were big concepts with kinetics, rates of reactions, equilibrium constants, and then applications of equilibrium constants was both 16 and 17. One was acid-base related, and one was pretty much everything else, including titrations and solubility products and things of that nature. All right, so let's talk reaction mechanisms. We've got multi-step mechanisms where we're given a couple of reactions and we're told this mechanism is the thing that we think is going to get us to our goal, right? And then when it comes to those reaction mechanisms, we have to know how quickly the steps happen. So, in the case of one where we have, let's say, 2, these are my proposed reactions. I'm going to draw my arrows a little bit better. Makes. These are pieces of information you'd have to be given. At the very least, these two, right? If I asked you for the overall, what would you do? Just add them all together. That's all you have to do is add the two reactions together and simplify. You've done it before. So we add them together and then we simplify by crossing off what's on both sides. Yeah.
Oh, it's kind of like the net ion.
That's how you determine the overall equation. So there's my proposed overall reaction. In the past, when we've said, all right, write me a rate law just given this information, how do we usually write them? No, that's K. Rate laws start with rate equals rate constant times something. Concentrations of reactants, right? Because the reactants have to disappear in order to create products. So this is what we would typically write. Okay. In a multi-step mechanism, however, we have to take into account the slowest step because the slowest step determines the goal, right? The slowest step is how fast you can go. So in reality, this can't work. There's no carbon monoxide in my slow step. So instead, we're going to use the slow step to predict the rate law. So if I was writing a rate law using the slow step, what would I write?
Rate equals K1. NO2 squared.
Times NO2 squared. That would be the proposed rate law for a multi-step mechanism with a slow first step. Remember that with slow first step, you just use the reactants in that first step. You should not have any intermediates if the first step is slow. However, we did talk about what happens if the first step is fast and the second step is slow. You have to write rate laws, you have to cancel them out, you set the forward reaction equal to the reverse reaction. You probably have vague recollections of how we did this in class. Yes, ma'am?
Do you think that on our final we're going to have to determine what's the intermediate and what's the catalyst?
I mean, for this type of a reaction, if I said, what is the intermediate, what would you say? The NO3, right? Remember, intermediate means produced then immediately used, okay? Are there any catalysts here?
No, because NO2 is already...
Technically, since NO2 is part of the reactant of that slow first step, one of them could be considered the catalyst, but you wouldn't get it wrong if you said no.
Okay.
Does that make sense?
So, okay.
Because you wouldn't be wrong if you said yes, but you wouldn't be wrong if you said no.
Yeah.
It's a weird interaction for this one. If I gave you one that had a catalyst, it would be obvious.
Yeah.
It would be here, and then it would be here.
Yeah.
Right? Like, and it would be something that you saw go away. It wouldn't be in the final reaction. If it's in the final reaction, it can't be considered a catalyst. Yes?
And then the intermediate, something that just shows up in the middle, then kind of disappears by the end. Like it wasn't
Right.
there initially.
So it's something that got produced and then got immediately used.
Yep.
As it's produced, it's used.
I'm going to have three-step equations.
If you did, the first step would still be the slow step.
Okay.
So even if I added one more step, the first step will be the one that determines your rate law. Yeah.
Can I use the restroom?
Yes.
We're not going to have to do like that, all that work.
Correct. Not for the slow second step. All right. We talked about catalysts. That was section 7. We talked a little bit about the lock and key model of catalysts. We've already talked about them a little bit while we've been reviewing, but the only thing I'm going to add is that enzymes are catalysts. Don't forget that. And that very typically they use what we call the lock and key model. So in order for something to be considered a catalyst, remember, it has to kind of stick around forever. In our enzymes, they can be reused over and over and over again. Really what they are, okay? So let's say that this is my enzyme. Its job is to speed up a reaction. And by that I mean create a space dedicated for the reaction. So if you think about the soup that is your body, okay, it has a lot of compounds, a lot of things going on. If we want a very specific process to take place, we want two things to collide in exactly the right way in order for that process to take place. Enzymes give them a spot, right? So let's say we have one piece that kind of here's one piece, and then I have another piece that comes along and it fits in here, right? What the enzyme does is create a spot for, we call this a substrate. The whole thing breaks apart into its products. This is like a fun diagram, right? So here's the thing that's coming into the enzyme. Enzymes can either put things together, take things apart. It kind of depends on the enzyme, but let's say this guy comes in. After the enzyme does its job, the substrate breaks apart into its two parts and makes two products, right? Whereas if we were trying to do that just in like no man's land in your body, where anything can happen, it would take a lot longer for it to occur. Not longer like the reaction takes longer, but longer for it to even be able to occur, right? Think about the needle in the haystack. Your body doesn't like to deal with needles in haystacks, so it creates optimized ways to create what it needs, right? And this is one of them. So we say it's lock and key because the substrate has to fit exactly into the enzyme in order to work. Once it does that, it can actually break apart, or it can form. It kind of depends on, again, if we're putting two things together or if we're taking one thing and breaking it apart. Okay? Lock and key is just a fancy term for the shapes have to fit. All right, moving on to chapter 15. Equilibrium.
Yeah.
And this was your daily cue. They like lowercase k and capital K. What can I tell you?
Yeah, why that one?
Because M was already taken?
Yeah, but like, so maybe I see.
All right. What is equilibrium? Start there.
When the reactions equal.
When the forward of the reaction equals the backwards of the reaction. Forget how that works.
Forward rate
Yeah.
equals reverse rate. We introduced this arrow that indicated things are reversible. Okay. When the forward rate equals the reverse rate, we are at dynamic equilibrium. What does dynamic mean?
It's ever changing.
It means movement. Let's go with movement. Not boring. Let's go with not boring. How about that?
I said really cool.
There you go. What's up?
Does that mean eight actually means movement?
Dynamic means it changes. Right?
Sure.
Wait, what did you
Don't throw that peanut butter and jelly across the room, Zach.
No. It's dynamic.
Because it's dynamic duo.
Because dynamic.
He's like movement day, and he said that was, you know. All right.
I
So,
wasn't paying attention.
dynamic equilibrium, when it comes to chemistry, means that the reaction actually never stops moving, right? Things are always being formed, things are always being reversed. We're never going to see molecules stop reacting. That's not a thing, okay? Dynamic means constantly happening, constantly changing. So please don't say, oh, it's at equilibrium, so it's done. That's not a thing, okay? 15.2 introduces the equilibrium constant, K.
Oh, really?
Capital K.
Because that makes such a difference. Just can't tell the difference.
They look the same too. Like,
Not with me.
It depends who you are and how you write it. Like yours are pretty good. I can understand the difference. But
Those are
mine-
two different letters, guys.
They are.
Yeah.
I mean, they're technically the same word. It's just
Yeah, we make it look kind of cursive, so that's.
You should wait till physics. There's a lot of M's.
Oh, that's nice.
wait, is that top one? Is that just like a lowercase k or is it supposed to be like fancy?
Wait, those first two are different from each other?
Yep.
Oh god.
Oh.
So you can write in italics.
I try.
I don't think I've ever actually written in italics.
No, in physics we focus a lot on like subscripts. So like, you will very rarely see me write something on the board without a subscript in that class. Because they all mean something. Like, potential anti-gravitational,
Nice.
mass, gravity, height. There's a lot of subscripts in that class. All right, equilibrium constant K says what? How do we write it?
Products over reactants, right?
Yes.
Concentrations of products over reactants.
Let's go back to our old favorite.
You.
little C, big C.
Let's go back to our old favorite. Ooh, products over reactants. Oops. I'm doing this backwards. Why is that subscript a C?
Constant.
Nope.
Concentration?
Concentration.
Hmm.
What's the other one I can write? P.
Oh.
K-A, yes, but you're in a chapter ahead.
Oh, that was just
Don't move forward yet. The other thing we can use is pressures.
Oh, yeah.
Oops, this is C. can use pressures instead of concentrations. You don't remember that?
That's the pain in the butt when you actually
Just
have to
saying.
find out the individual things.
Have we ever actually used that?
Pressure?
Yeah, we had it on one of our tests too.
We did it. All right. Let's talk about values of K. So this is going to be an indicator of what is happening at equilibrium. Remember that this is at equilibrium. Okay? This is equilibrium. Outside of equilibrium, what do we use instead? Q.
No, and then there's this one.
Oh, this one's not so bad.
Q1, but I don't remember.
1, 2, 3.
And the same thing for QP. But I'm not going to write it down. Okay. Let's talk about what they mean.
It's the same thing for QP, like, I missed.
Correct, yes, for just...
Yeah.
Ooh, I know what I'll do. Quotations. All right. What does K very, very large mean? Product favored. What does K very, very small mean? Thank you. Excuse me. All right. So this is what K means. What do we use Q for?
Compare.
To compare. At some point in a chemical reaction. Yes,
Is this where it's Q is greater than?
correct.
Okay, and then
Q is greater than, equal to, or less than. Correct. Sorry, I'm going to erase this one. All right. Oops. Okay, so if Q is at any point in time other than, well, I guess let's just go with any point in time. What does it mean if Q is equal to K? That we are already at equilibrium. What does it mean if Q is greater than K?
Shift to the left.
It means that the reaction must form reactants. In other words, we talk about which direction the reaction needs to form or go in order for it to get back to equilibrium. If Q is less than K, then
Must form products.
we must form products. AKA, we must shift right. When something is disturbed from equilibrium, what principle is that referred to as? That is correct. This is all Le Chatelier. Yes?
Do we have to write our own formula sheet, or are you giving us?
No, I'm going to give you one.
As long as
Fine.
you kind of do it.
All right. So what does Le Chatelier's principle actually state?
That is
If products or reactants are introduced, it must shift in a certain direction.
Right. Disturbances from equilibrium must be shifted to achieve it again. IVE? This is a big one because we use it in several chapters after this. Okay? So Le Chatelier is like introduced here, and then we basically manipulate K over and over and over again in various ways in other chapters. 16 and 17, still using K. Okay, all right. Next thing we introduced in this chapter, ice tables. Oh, yeah. I stopped writing sections, but I'm in like section 6 or 7. Whatever. All right. Ice tables. All right, so here's our reaction. We used ice tables to calculate a bunch of different information. One of the things we could use them to find was K, right? I'm going to just put empty brackets, so concentrations we could find. At equilibrium, we could find concentrations. Initial. At some point, we use these to find pH, POH, things of that nature, titrations, all that. All right, so we're going to start here. The question says a 1 liter flask is filled with 1 mole of H2 and 2 moles I2 at a temperature that doesn't change. We're told the K for this reaction is 50.5. What are equilibrium concentrations at, oh, that just makes sense, of all three? Okay. What does I stand for? What does C stand for? Change. Initial. Change. Equilibrium. Okay, so we're given initial information, right? What were we told?
1 mole H2, 2 moles I2.
So we know the concentration of H2, initial, and we know the concentration of I2, initial. I say concentration, but remember, you have to actually get it into moles per liter to put it into the table. We did do some where we said you could leave it in moles and then convert it to the concentration at the end. In this case, since it's 1 liter, the concentration is just the same as the molar amount. So we do 1.00, 2.00. If we weren't given one to begin with, what do we assume it is? 0? Yeah. So, I thought someone was trying to say something. Yep.
To use ice to find it, is that a K1 value or is that
Just K, comma. Sorry. I was trying to make a list of things, of reasons why or how these ice tables are used. All right. What do we do next? Yep. What gets on the left and what goes on the right? Minus X here, right? Because we have to subtract reactants. What about over here? Plus 2x. Don't forget coefficients go in front. Okay. Then at equilibrium, we know you did not get to ignore changes in X until chapter 17, boys and girls. Did a lot of math. All right, what do we do with them now?
make the reactions equal?
We have to write a rate constant expression, right? Or an equilibrium constant expression. K equals products on top squared because of the 2, right?
See, this is where I start not liking this class.
What were we told K equals?
50.5.
That, boys and girls, is a quadratic equation.
That's
There's no way to do quadratics on the plan.
You're probably going to have to do at least one. We did so many of them.
that's fine.
I can't tell you that you're not going to have one on your final exam.
No. I think you should say
Sorry.
that we don't because we had so many.
Yeah,
I mean, I can lie to you.
we clearly have a lot of practice with you.
But we did so many of these, why would I ignore it?
Well, like,
That doesn't make any sense. All right, quadratic. If we solve it, I'm just going to skip ahead to what x equals.
We skip ahead to what is equal to the final.
What?
Then just not use the quadratic.
No.
Oh, okay.
I need to steal that back from you. This is Valentine's. I really don't my calculator.
We skip ahead. We know what x equals. What do we do with that information? Our goal was what the concentrations are at equilibrium, right? So we have to plug it in here to figure out what our equilibrium concentrations is. For this first one,
I know. Funny.
do not forget to take this number and do the last step. Getting here gets you the 4 out of 6. Getting here gets you the 6 out of 6. Okay? Does that make sense? Don't forget that step of going from I solve for x to the equilibrium. You've done this much work. Don't forget to answer the actual question presented. Yes.
When I do ice tables for the one that has 0, I usually just like draw an arrow like from the 2x down. Is that okay?
Yeah.
Or do I have to write it?
I don't really care about your ice table. I want your ice table to be there. But you use it however you need to use it.
Okay.
I don't care. All right. That was chapter 15. Take a break. You get 4 minutes. We got 16 and 17 next. 8:56. At least 2 more, but I wanted to get through 3.
We can get the 3. I have faith.
Not if we have to talk about acid bases and titrations.
Oh, we can just climb over that. That's easy.
You know, this would, like, if you just, like, skip titrations on the final,
Part
then
2.
you won't have to talk